require the funding from all countries. No single country can do this. So all European countries, United States, in fact India also has contributed, whoever according to his capability, has contributed to produce that machine. And how high energy it has developed? It has developed a reasonably high energy up to, so that with that energy we have been so far able to probe a microstructure which is 10 to the power minus 18 centimeters. Remember, 0.1801 centimeter is the smallest structure that we have seen with that object, with that wave. I talk about this. So, we have spent this money. Do you know the amount of money is 10 times the rocket mission which was sent to moon? You may ask that by seeing the microstructure, what we are trying to do? Why all countries have united to do this? To look into this microscopic structure. And next question you may ask, of course, that can I increase the energy even more and take it to 10 to the power minus 30 centimeters? Can we do it? I mean, smaller and smaller and smaller. The answer is yes, we can, but it will need an amount of money which is absolutely incredible. So the question is that, why should we do this? Now, to answer this question, I'll give you two answers. One answer is, in fundamental science research, you cannot always ask why do you do it. Because you probably many of you know that when electricity was first discovered by Benjamin Franklin and Michael Faraday, when they were asked that what is the use of this, they told that before our answer, I would like to ask you what is the use of a newborn baby. So these are newborn babies in science. And today you understand that if there was no electricity, we wouldn't have survived. Our life is controlled by electricity. So why do we want to see this microstructure, this small structure? What do we expect to get in future? This I will tell you. And till this point of the story, you have no clue that where is Higgs boson here? Where is that God particle? But that will appear. See. Now, one natural question is that suppose you go inside somehow and try to get these small structures. Suppose you go inside and see microscopic objects. Suppose you go to molecular level or even smaller atom or even smaller proton, electron, neutron. Question is, what are the rules and laws followed by these microparticles? What are the rules and laws they follow? Now, all of you know, because you are all 19, that any ball, take a cricket ball. If I ask you what laws it follows, take any object that you see around you. All of you will answer, the law is Newton's law of motion. The force is mass into acceleration. You will solve anything, put mass, put force, you get the acceleration of the object, how it moves. But unfortunately, as you go inside, you are made up of atoms, you are made up of electrons, protons, neutrons. They do not follow Newton's law. So this is surprising. You may say, I am following Newton's law, my motion is governed by Newton's law, but by the object with which I have been built up of, they are not following Newton's law. It is because they are following a different law, this microscopic thing in your body, but when you take the sum of that, it becomes Newton's law. So you are a macroscopic object, large object. Your behavior is an average of all the microscopic things. And that microscopic things, they follow a certain law whose average is Newton's law. So what is the law they follow? They follow basically two very important principles. One is the quantum theory and the other is special theory of relativity. Now these are the two spectacular discoveries in the last century, that all the microscopic thing by which everything is made up of, what kind of law they follow. They do not follow Newton's law. So with this in mind, for today's lecture, I don't go into details of quantum theory because it is not that much important for today's discussion. It's very important, but not for today's discussion. But for today's discussion, special relativity is important. And I will be spending little more time on that. Okay. But I will tell you very briefly that what the quantum theory is, because this is something which you need to know. Quantum theory is a very strange theory. It tells you at the microscopic level that nature can only be described statistically with some uncertainties. So what does it mean? Try to understand, when Newton was proposing his laws, what did he do, or what do you do? You say that take a ball in your hand, you throw, the force given by you on the ball is equal to its mass into its acceleration, right? That is Newton's law. But my question is that how do you know that this is correct? Suppose I take a ball, I throw it, and I tell you the amount of force that I have given to the ball is equal to its mass times its acceleration, where the way it is moving, and then you can find its trajectory, how it's moving. But I want to ask you, how do you know this law is right? You will say that fine, I will throw a light on the ball, this light will go to the ball, it will be reflected from the ball, you will measure in what direction, thank you, in what direction it is traveling, in what direction it is traveling. Okay. And you will check whether Newton's law is working or not. You will verify that it is traveling in a path. But have you ever thought one important thing? That when you are seeing that the object is moving, suppose the train is moving in front of you, the train is following Newton's law. The force given by the engine is equal to its mass into acceleration. But my question is, who is seeing this? You will say, I am seeing this standing on the platform. I say, how do you see this? You will say, I throw a light is reflected and coming from the train, and I see that how the train is moving, and I check that whether Newton's law is correct or not. But now if I ask you, that suppose, how do you know that when the light is falling on your object which you are observing, that light is not giving it an impact and not changing its motion? Then you will be very puzzled by this question, because if I tell you that I am walking on this stage and you are seeing me, now I am claiming that your process of seeing me by throwing a light on me can change my path. Then you will say, okay, then that's a problematic thing. Because I don't know how the light is going to hit me and go to your eyes. So you will say, okay, I won't see you. You will say that I don't want to see you, but I know that you are following that path. I will say, how do you know this? If you don't see me. So, quantum theories say that the meaning of knowledge is the object and we, the observer, we interact with each other and produce a knowledge. But Newton thought that knowledge exists with the object and we just observers see it, but in the process of our seeing we don't disturb it. But quantum theories say you may disturb the whole entire thing. But now can you imagine that when light falls on the car plying on the street, do you think that the light can do anything on the car? How much energy the light has so that it can remove the car from its path? The light is hitting the car. It never happens. So we can neglect that effect and we can say Newton was right, there is no impact of our observation on the system. But if the system is not a car but it's an electron, then the light that will fall on the electron will hit the electron and push it from its original path to some other path. So your process of observation will disturb the system. So they develop a new theory called quantum theory, which says that your process of observation generates some uncertainty of its motion because you don't know how you are going to disturb it. And you develop a statistical description. One day I will talk only about quantum theory, then I will tell you much details. It is such a fascinating subject, but this subject was proposed and finally developed by these three great people, Schrödinger, Niels Bohr, Schrödinger and Heisenberg. They are some of the masters who developed this brilliant idea. Do you know one very interesting story I tell you? When Einstein first heard this, Einstein told them that, see, you are saying that when the ball is moving, you are trying to see it and in the process you are disturbing the ball. And the disturbance is making its path uncertain. Therefore the knowledge is uncertain. So, I am ready to believe it. Einstein said I am ready to believe it. But suppose if I don't see the ball, then the ball was certainly following a definite path because I have not disturbed it. Then this quantum theorist told him that how do you know that? You are seeing me in this room, right? Suppose all of you leave this room. Can you tell me that I am still in this room? You believe that I am still in this room, but is there any proof? So these people developed a new philosophy of science. I don't want to get into details of all this because today my objective is different. But this subject was a revolutionary subject called quantum description of nature. So they developed this, that how to take the effect of your observation on the system. And therefore, what is the conclusion of this subject? That this pain which you are seeing, it does not exist without you. It exists because you observe it. But Newton thought that you observe it, that's a different thing. You may or may not observe it, but this exists. But these people say that there is no proof that they exist if I don't see it. So this new subject completely fascinated the whole world, and it turned out to be correct for the microscopic particles. I will stop talking about quantum theory at this point. I will take your questions later if you have more. But quantum theory is something, this kind of a very strange subject which takes care of the disturbance. But then comes relativity. This is the other thing that we need. And this thing we need very, very importantly for describing Higgs boson. Okay. So probably you are thinking that where is my Higgs boson? It is not coming into the story. Wait, it will come. I assure it will come. So what is relativity? So those who have attended my last day's talk, I talked briefly about relativity, but today I will repeat because there are many more students here. So I talk for them in a simple way. Relativity is basically a theory of time. Suppose I ask you that, do you know what is time? You will say, of course I know, there is a clock in my watch in my hand, it is ticking and time is flowing. I will tell you that take a little more time to think about time. Time is very, very serious. Firstly, can you go in the reverse direction of time? Yes or no? Can you? There should be one answer. Is there anybody in the audience who can go back to the past? Answer is yes or no? Yes, I can't see. I don't understand. What is the answer? How many people think that you can go back in past? So I don't think it's anybody. Because then I would have called you on the stage and would have requested you to show in front of everybody that you can go back to the past. So you cannot. Time is taking us towards future only. So Einstein said that Newton thought that for all of us there is a time which is something very universal and it is ticking forward to the future, and for all of us we have the same time. We all have same time. We can synchronize our clock. But Einstein said time for different observer or different for all of us are different. This was Einstein's statement. But you will say that why Einstein is saying this? Because we can certainly synchronize our clock, then you will see all of your clock are same. But I will show you that actually what you are doing is not exactly correct. You cannot do that. Let me show you. It starts from so time is not universal that everybody will have same time. There is no universal clock. Just as everything has their own position in space, you are sitting here, you are sitting there, you are sitting there. Each of them has their own time. Time is also like a coordinate, just like everybody in space has a coordinate. And just as position is relative, you are nearer to me than the person sitting at the back. The flow of time can be slow or fast. Time clock doesn't run identically in everybody's clock. You might be very, very surprised to know this, but I will show you. So how do you know this? How did Einstein prove this? This has been proved experimentally, so no question about challenging it. It started with a very strange observation. Consider there are two objects A and B. It is travelling with a velocity v1, it is travelling with a velocity v2. This observer sees that this is travelling with a velocity v1, means this observer sees that it is travelling a distance v1 in 1 unit time. And this observer sees this travelling a distance v2 in unit time. That is the meaning of velocity, the distance travelled in unit time. So my question is to you that what is the velocity of B as observed by A? What is the velocity of B as measured by A? Any answer? Please feel free to talk even if something is wrong. Don't hesitate to talk wrong things. V1, sorry? V1 plus V2. Okay. So how do you know that this is V1 plus V2? Because, listen very carefully. You have to give an explanation that why do you know this V1 plus V2, why not V1 minus V2? It is because, see, this has travelled a distance V1 and this has travelled a distance V2 with respect to this observer. So distance between them has been reduced by V1 plus V2. Right? So this A, who says that I am not, suppose this is a train and you are seeing another train coming. So you say I am not moving, this is coming with a very high speed to me because our distance is getting reduced V1 plus V2 in unit time. So he will say our distance is getting reduced by V1 plus V2 in unit time, and what you have said is right, the relative velocity is V1 plus V2. So this is the prediction of Newton's law also. But it turns out that if B travels with speed of light, suppose this travels with speed of light, this is travelling with speed of light. Okay, this is C. Then the speed of B as perceived by A, according to your formula, should have been V1 plus C. But it turns out to be same as C. Now this is very, very strange, because if this observer see traveling a distance c, that is c distance in unit time, how is it possible that he moving with this distance v1 in unit time also will say that it is traveling with same velocity? This is absolutely amazing, because if this observer says this is traveling c distance, and this observer is moving v1, so distance is getting reduced by v1 plus c. So it should have been v1 plus c, as you correctly said. But he says this is also c. Speed of light is not changing whether you are static or you are moving. So here we needed a genius like Einstein. He said that this can be explained only in one way. When you are saying this observer seeing its speed c in unit time and its speed v1 in unit time, you are saying that their distance is getting reduced by v1 plus c in unit time. The error is that how do you know that his unit time and his unit time are same? If the clock runs differently, if his clock and his clock runs differently, then its definition of speed is distance by time. If the time runs differently, then it is possible that these times are related in such a way that this sum will still be c. Because the distance by time thing, the time factor has changed.